안녕하십니까. 기조 강연 연사를 소개 맡게 된 아주대학교 금융공학과 배형욱입니다. 먼저 엄상일 교수님께서는 그래프 이론과 이산수학에 대해서 훌륭한 업적을 많이 생산하셨습니다. 그리고 1998년 한국과학기술원 수학과를 학사 졸업하시고 2005년 프린스턴 대학에서 응용 및 전산수학에 대해서 박사학위를 수여받았습니다. 그 이후 2008년부터 현재까지 카이스트 수리과학과 교수로 계시고, 또한 작년 2018년 12월에 기초과학연구원 수리 및 계산과학 연구단 이산수학 그룹의 칩 인베스티게이터로서 활동하고 계십니다. 그리고 2012년 12월에 젊은 과학자상을 수상하셨습니다. 그리고 발표하실 제목은 How to Decompose a Graph Theory, a Graph into a Tree-like Structure. 훌륭한 강연 부탁드립니다.
네, 방금 소개받은 엄상일입니다. 먼저 이렇게 기조 강연을 할 기회를 주셔서 대단히 감사드리고요. 아주 영광입니다. 네. 중간에 내용은 영어로 스위치를 할까 싶습니다. 어떤 분들께서 영어로 좀 제발 해달라고 부탁하시는 분들이 있어가지고요. 먼저 제가 소속이 이제 2개라 가지고, 그리고 또 IBS에서 항상 IBS를 먼저 적어달라고 요청하는 바람에 이렇게 카이스트 교수님들께 죄송하지만 1번은 IBS, 2번은 이렇게 카이스트 이렇게 적어놨습니다. 현재 궁금해하시는 분들이 많을 것 같아가지고요. 제 사무실은 바로 여기 이쪽 코너에 있습니다. 아까 어떤 분께서 창문이 많은 방이 좋은 사람들이 쓴다 이랬는데, 예, 코너라서 창문이 많고요. 여기가 이제 내부의 모습입니다. 많이들 와주셔서 활용을 해주시면 감사하겠고요. 참고로 수리 및 계산과학 연구단은 여기 2층 전체를 배당을 받았습니다. 현재 IBS 이 건물 전체에 출근하는 수학 박사는 저 혼자뿐입니다. 그래서 제발 많은 분들께서 와주셔서 1년 내로 수학 박사 출근하는 수가 10배가 됐으면 하는 그런 마음이 있습니다. 많이 와주시기 바랍니다. Alright. So let me begin. So this talk is about decomposing a graph into a tree-like structure. And so first part of my talk will be the motivations, why we are interested in decomposing some structure like graphs into a tree-like things. All right, so here are some motivations. So basically in graph theory or in many practical areas, we have some problems to solve, but we have problems that are proven to be difficult. So, which we call NP-hard, like for instance, the coloring problems of graphs, or the finding largest independent set, or finding a Hamiltonian cycle in the graph. These are the problems which we don't know how to solve it, and which we have a proof that if we can solve any of these, then we can solve many other difficult problems, so which is called the NP-hard. But in reality, we actually want to solve it anyway. So this is one cartoon in the book by Gary and Johnson, and even though we know by the theory or by mathematics, we know that these problems are hard, we still want to solve it. So how can we find the positive solutions? And one way to solve it is actually restrict our attention. So imagine that we have a problem like coloring or independent set or Hamiltonian cycles. Well, it may be difficult in general, but if we restrict the input graph to be a particular class of graphs, like trees, well, trees are simple, so probably any problem will be easy on trees, right? So if graph is like a tree, it should be easy. When people have studied many special classes of graphs, like planar graphs or interval graphs, or whatever that is, and for each of these classes of graphs, we studied each of these problems, and people were writing papers like you pick one problem of your favorite problem, and you pick one input class of graphs, and then you find an algorithm that solves this. So the number of papers we can write is like product of these two. If you have 10 problems, 10 graph classes, we can write like 100 algorithms, each specific to specific problem and specific input classes. So this was typical approach, and then later, people realized that, well, in some cases, in some of the graph classes, they have some common features. If you can unify them into something, then we may be able to find a unified algorithm. So not all classes have such a property, but for some of them, they have a common structure, and in many cases, it has a tree-like structure, which we call like tree-like structure with small width. I will describe what that is later. And then people write papers like, well, I can solve coloring problems whenever the width is small. Or I can solve this independent set problem whenever the width is small. So instead of writing one algorithm for specific class and specific problem, now we have a one unified algorithm for covering many classes of graphs. But for each problem, you have one unified algorithm, right? So now the number of papers you can write is reduced a lot, like number of problems times 1. So that's one motivation. So we want to find some common unified structure of graph classes that could be useful to find an algorithm. And actually, we can do more. There is something called the Meta Theorem, where you can not only unify the classes of graphs, you can also unify the problems. So there is a theorem called the Croissants Theorem, which essentially says that any graph problem which can be expressed in certain logic can be solved efficiently whenever the input graph has a small width. But here the condition is that you have to be given particular tree-like decomposition as an input together with the graph. So the motivation of this talk is to provide such a decomposition. Right? In order to use this kind of theorem, we need to have an algorithm to generate tree-like decomposition in order to apply this thing. Okay, so that's the one motivation. There are other motivations, but I will skip them. So what are they? Right. So the second part is the definitions, some definitions. So I will give you 3 examples of the decompositions, which graph theorists like to study. So the first example is called the tree width and tree decompositions. And this is the most well-studied width parameter in graph theory, which was introduced by Robertson and Seymour in 1986. But the similar concept has been studied earlier. So suppose we are given a graph like this. So you have a 9-vertex graph here. And tree decomposition is a pair of a tree with a collection of bags. So bag is a set of vertices for each node of the tree. So it looks like this. So this is one example of tree decompositions where each bag, so each node of the tree has a set of vertices. So like this one has 1 to 3, this one has 1, 4, 3, etc. And there are 3 axioms to satisfy. I didn't write it down. So one of the axioms is that every edge, at least one bag should contain both ends. Like for instance, 2, 3 is an edge here. So here you have a bag containing 2, 3 at the same time. And another condition is that whenever you look at the particular vertex, for instance, vertex 9, then they form a subtree in a graph. Subtree. So in this case, you look at 9, 9, 9, they are not disconnected. Right? So this is another condition to satisfy. So if we have a tree decomposition, then anything could be a tree decomposition. But we want to find the good one. So what are the quality measures, which is called the width? So width of tree decomposition is the size of the largest bag. -1. So this -1 is their mistake to add -1 in the definition, and their intention was to make sure that trees have tree width 1. So whenever graph is closer to be a tree, then you get a lower number. If graph is far from being a tree, then you get a larger number. And tree width of graph is a minimum possible width over all possible tree decompositions. Now, if you look at these definitions, it's clear that there are many, many tree decompositions, and if you want to look through all tree decompositions, then it's going to be impossible to compute the tree width, right? So the definition looks quite ugly in a sense, but later we will see how to decide tree width efficiently. So this is one instance of decompositions. There's another one. This is called the branch width or branch decompositions, which were also introduced by Robertson and Seymour, same people. And so in this case, now you have a graph. So this is a graph. I put labels over the edges. So from A to L, M, N. Yeah, from A to N, I have labels. And the branch decomposition of graph is a pair of a tree with a maximum degree 3 and some labeling of the leaves by the elements of the edges. So for instance, this is one instance of the branch decomposition. So you have a tree, so each internal node has degree exactly 3, and the leaves are labeled by the edges of the graph. So anything like that is called the branch decompositions. And then we also have a measure how it is simple or complex. So if I look at, for instance, one edge of the tree, then I look at the partition of the vertex, the edge set of the graph. So here you have A to H and I to J. And then let's look at the corresponding edge set in the graph. So on the left-hand side, you have green edges from the left. On the right-hand side, you have the red edges from the right. And then what we count is the number of vertices meeting both sides, green and red, at the same time. So here you have 2 vertices meeting both green and red. So the width of this edge is 2. Now I can compute this width for every edge of the tree. There will be some maximum number. So that number is the width of the branch decompositions. And then the branch width of graph is the minimum width of branch decompositions. So this is, well, it's annoying that I have to give this definition all the time, and nobody seems to understand, right? It's complicated. There are lots of max and min. But basically, the whole idea is, well, suppose you have a finite set of elements. Now, what I want to do is to cut it into half, and cut it into half, 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 all the way until every single piece is a singleton. Right? So here's one example. I cut it into half, cut it into half, half, right? So I cut. I mean, you have a cake, we want to cut it somewhere, until every piece is singleton. Now, what is that? Well, how can you represent that? Well, naturally, what you get is a tree. When you take a dual of this, you get a tree where every internal node, every region is bounded by 3 cuts. So when you get this, a tree with every internal node having degree exactly 3, and leaves are labeled by this singleton. So that's the motivation of the definition of branch decompositions. So instead of studying graphs, you can do it for any finite set. Like for any finite set E, I can talk about branch decompositions, and then we can talk about the quality measure. Well, how do we measure the quality of the cut? So let's define some connectivity functions. So I will define anything with satisfying these 3 axioms to be a connectivity function. And then people call connectivity system to be simply a pair of finite set with some connectivity function. So we can study not only graphs, but many discrete structures. So here are then we can extend the definition of branch width for connectivity system. So everything is same, except when you measure the width, instead of looking at the graph, now you look at the value of the connectivity function arising from these partitions. And then we take a maximum, and then branch width is minimum possible width of the branch decompositions. And this definition allows us to generalize the other situations. So whenever you use different connectivity system, you get different definitions. So here is the one example, like if you count number of vertices hitting both sides, the x and complement, then you get the usual definition of branch width. If I count edges from set of vertices to the complement, then we get definition of something called the carving width. If I count the rank of the matrix whose rows are indexed by the vertices in X, columns are indexed by the vertices not in X, and if you put 1 if they are adjacent, otherwise not, otherwise 0. And this matrix, the rank of this matrix happen to be connectivity function, and we call rank width of graph. But these are all from graphs, but this is one example from vector system, vectors. So suppose you have a collection of vectors. Now, if I take a subset of vectors, well, I can look at the span of the my set X and the span of the complement and take an intersection. So that's some subspace. And compute the dimension of that. That happens to be also connectivity function. We can define that to be some width, and actually this is equivalent to branch width of a matroid over, which is represented over some field. So this is not, a matroid is more general object than vector space, but I will call it branch width of matroid for this talk. Right, so for any of these objects, we have corresponding interesting decompositions. And then problem is to find the decomposition efficiently. Right? How do we find the general algorithm that finds the decomposition of small width? Because we need it for our algorithms, or we need it for some theory, etc. So this is the part 3, so the main part of the talk. Right. So the bad news, so let me start with the bad news. The bad news is that this also is NP-hard problem. So if I'm given a graph, and if I'm asked to compute the true width of this graph, so what is the minimum k the graph has true width and most k? Well, this is already known to be NP-hard in 1987. And for carving width and branch width, all these things, it's already known to be NP-hard. So we cannot hope to have an efficient algorithm if we don't fix k. Right? If we don't know the, if somebody asks, like, is true width at most 10, 11, 12? If that's different problem, but if somebody asks, what is the true width of this graph, then it's a difficult problem. But the good news is that when you fix k like this, then there are algorithms available. So I will start with the approximation algorithm, and then something slightly better, and then something weaker, and then something even worse. But if time permitted, I will go through every one of them. So, right. So let me start with the approximation algorithm. I want to give you some idea. So the problem of finding decomposition of width at most k is typically difficult. So what's an easy problem? Well, the easier problem is to find the decomposition of approximately, small, right? So I want to have an algorithm that for any fixed k, we find the decomposition of width at most some function of k, or the algorithm confirms that we will never have decomposition of width at most k. So the width is bigger than k. So how do we do such a thing? Well, typically, we employ the greedy algorithm. So imagine that I know the tree structure on the left-hand side of this bag. So this pink area is the current cut. And how do I split the right-hand side? That's the problem. We want to keep splitting into half, etc., right? We want to find the small cut. And the idea is, usually we try to find a small separator or small cut here. And if we find it, we will split into two sub-problems. So here you have a pink cut and yellow cut, and then we recurse. So this region is getting smaller, so we rerun this algorithm again and again. Eventually, everything gets singleton. And this sounds too good to be true, right? So then what's the problem? I mean, isn't it so trivial? The difficult part is to make sure that, I mean, we are not starting from the optimal decomposition. So this could be arbitrary cut. And we need to have a theorem saying that if you cannot find the small separator here, then the width is big. So that's some mathematical theorem we need in order to make this algorithm work. So that's typical approach. And for tree width, people have been studied a lot. So in 1995, Robertson and Simmer came up with a square time algorithm that generate the 3D decomposition of width at most 4k plus 3 if the input has width at most k. And then the running time has been getting faster and faster, right? So n squared, and then next people came up with n log squared n, and the next people came up with n log n. Then in the end, Hans Bodelander in 1996 came up with n linear time algorithm. I mean, you look at this years, that looks quite weird, but you know, these are the journal papers, and the stock is a conference paper. So it took, I mean, even though this was studied earlier, but the conference paper always appear quite quickly. So this is the current best approximation algorithm for tree width. And for branch width, the 1995 paper by Robertson and Simmer actually was written in terms of branch decomposition. So they also had a algorithm for both branch width and tree width, and this has same running time, n squared. And then you can look at the same problem for matroid. Like, what if you have a vectors? What is the, I mean, how can you approximate the branch width? Peter Hilani had an algorithm that runs in cubic time, and the ratio, approximation ratio is 3. And then I had an algorithm with Paul Simmer in 2006 that not only runs for graphs or matroid, but also runs for any connectivity system. So whenever you have a connectivity function for any finite set, we can find the branch decomposition of width at most 3k plus 1 in time n to the 6 times log n. So this is this generalizes all of these things. And for particular case, like for graphs rank width, we get the faster algorithm. So somehow, by some magic, even if the object you're talking about is not graph, whenever you have a symmetric sum modular function, then we can run this algorithm for approximating decompositions. Now, once we have this approximation algorithm, what do we do? The next problem is to determine whether or not the width is at most k. And if yes, if width is at most k, we also want to find the decomposition of width at most k. That would be, because we need it to solve the problems that requires decomposition to be given. So how do we do that? So typically, this is how people do. So we first run the approximation algorithm, like the previous slide, where you are given, you generate decomposition of width at most, let's say, 3k. If the approximation algorithm says that width is bigger than k, then we can simply forget, right? So if it confirms there's no decomposition of width at most k, then we are happy, we can stop. Now we are in a case where we're given some decomposition of width at most k, and here you have some tree-like structure already, but the width is bigger. So what we do is we use this tree-like structure to find the decomposition of tight width. So mean, I already mentioned that many problems become easier if the corresponding decomposition of small widths is given. And not only many other problems are becoming easier, but also the finding this decomposition problem. So the problem of finding decomposition of width at most k also become easier. So that's a strange part, right? We are trying to solve this problem A, and we have approximate solution for A, and we can use this approximate solution of A to solve the problem A. Okay, so it's an interesting approach. So there are two methods that I remember. So one is really indirect, but we use a lot of theory. So the first indirect method is to use big theory or some theory, mathematical theory, to prove that there are only finitely many obstructions, whatever that means. Like for graphs, people study graph minors, and there are theorems saying that whenever you have classes of graphs closed on taking minors, you must have finitely many forbidden obstructions. You can use that. For matroid, there are similar theories. So we use some theory to prove that for the property of having branch width at most k or tree width at most k, you must have finitely many exceptions or obstructions. So if you don't contain any of them, the width is at most k. If you contain any one of them, the width is bigger than k. Now, using that, we obtain yes-no algorithm to say width is at most k. Like we just check, does it contain this obstruction or not? For each of them. Since we have finitely many of them, we can check one by one. And for instance, we use this Meta Theorem. Like just write down the logic formula to describe whether or not I have obstructions. And this is possible in some cases. But this yes-no algorithm doesn't necessarily give you the decompositions. Right? Somebody says, well, is this graph planar? And someone says, well, yeah, it's planar because it doesn't contain K5, it doesn't contain K33. These are the obstructions, so it's planar. But then this person may ask, well, how can you draw? How can you draw it on the plane? Well, I don't know, right? Because I only knew that it doesn't contain obstructions, but that doesn't mean how I know how to draw it. So from yes-no algorithm, we may sometimes be able to generate the decomposition. So this is called the, this approach was studied for tree width and also for branch width. So this is an indirect method. And sometimes we can develop this specific dynamic programming algorithm to enumerate all possible decompositions and then use that to solve the problem. So instead of using any of these big theories on finitely many obstructions, now we don't use any of them. We use a specific data structure to make algorithm. So that's I call a direct method. So let's look at this problem. So we want to determine width at most k for fixed k. So for tree width, in 1987, 3 people, like Amber, Cornell, and Proskowski, proved that there exists an algorithm that runs in time n to the k plus 2 to determine whether or not tree width is at most k. And if k is bigger and bigger, then this will grow very quickly, right? Now, people want to have an algorithm that runs in n to the constant. And in a big O part, you might have some function of k. We don't care because so when I say something like O of n squared, that means I have some function of k and then n squared. Okay? And then in '86, Robertson and Seymour came up with an indirect method that they use big theory on graph minors to say that we can decide tree width is at most k in square time. And then McFellows and Langston had an idea how to use that yes-no algorithm to generate the decompositions. So this was done in 80s and 90s. And then in 1994, Baudrillard and Clark killed this problem by providing a direct algorithm that has a specific data structure for this treewidth problem and solve the treewidth problem completely. So for branch width of graph, in 2000, Dimitrios Tilikos and the same Hans Baudrillard has a paper that runs in linear time. And this approach was direct. I put this question mark because this was announced and it was on the preprint server, but never published in the journal because it's quite complicated. And then in 2008, Peter Hillani and myself had developed the cubic time algorithm for many of these problems, like branch width of matroid or graph, rank width of graphs, etc. And our method was very indirect as well at the time. So we had to use a lot of tools from matroid theory, and then we use some of this Meta Theorem as a black box. So we didn't really like it. And then recently, with my PhD student, Jisoo Jung and Eunjung Kim in Paris, we were able to find the direct algorithm to generate the decomposition for branch width. So which may have applications on data science because this matroid part is just a set of vectors, right? So we want to decompose points in the vector space in a way that the points are spread in a tree-like structure. So that's one place I am looking for. All right. So what is the key idea? So what we use is actually a lot of linear algebra. So we want to, actually this problem that I solve is over the finite field. If it's infinite field, we have no idea what to do. So in the finite field, everything becomes nice in a sense that the number of subspaces of a finite, constant dimension vector space is finite. So we can enumerate all subspaces, and that's nice. So that's one ingredient. So we only have finitely many subspaces, so I can enumerate all possible things. And we design some equivalence relation on solutions. So we come up with some encodings of solutions. And if some partial solution can be extended to full solution, and then another partial solution is equivalent to the first solution, then we were able to prove that they both extend to full solution or not. And there are only finitely many such encodings of partial solutions. So we can use that, and we use the tree structure to generate the solutions. So that's how we did it. Now, still, we have cases where we don't have any algorithm. We don't have any n to the constant algorithm. So, like if we have a general matroid, like points in the real vector space, you want to decompose by small branch decompositions, that we still don't know. We don't have any algorithm that runs in time n to the c. The best we know is this algorithm by myself. So we have an algorithm that runs in n to the 8k plus 6 times log n. All right? And here delta is the time to compute the connectivity functions. So we have an algorithm that runs in this time. So if k is growing, then this will get slower and slower. And it would be nice to have either we prove this or we prove that, well, in general, this is impossible. That would be nice. And now, this is a typical problem, NP-hard problems. And some people thought that maybe one way to investigate difficult problem is to come up with the exact exponential time algorithm. So there are people studying like Hamiltonian cycle problem whose algorithm is like runs in time c to the n, where c is extremely small, bigger than 1, but extremely small. So it's still exponential time, but the exponent is quite, the C is small, so in practice it may be useful. So for instance, for tree width, people had started to work on this algorithm. So even though there are lots of tree decompositions, these people made a 1.96 to the n algorithm, which is surprising, right? You don't even need to spend like 2 to the n time, right? And then Fomin and Billinger they were able to speed up to 1.73. And for branch width, we had an algorithm that runs in 2 to the n times polynomial. So it's interesting whether we can improve this barrier. So this is 2, and we have no idea how to improve it to 1.99. Right? So that is not clear. Right, the special cases. So for some special cases, we know how to compute things exactly. So for branch width of planar graph, we know that they can be computed in polynomial time. And we don't have many instances where this kind of thing is known. So that's the exact algorithm. So far, I have shown you the 4 types of algorithm, right? So one is approximation algorithm that generate decomposition of small width, but the width is better, slightly worse than our desired bound. And the second thing is the fixed parameter tractable algorithm, so that for some constant k, we want to find decomposition of width and most k. And the third thing is the general situations, like we have n to the 6k, 8k, and now this exact algorithm. All right, so that's all I have. So now I will show you 2 applications of these parameters. So one is in the quantum information theory. So somehow in 2007 or 6, I began noticing that some of my papers are cited in physics journals. So I was wondering what's happening, and turns out that they were studying the quantum computation on a graph state, something called graph states. And what they do is to define some computation model using quantum things, and this model has to be universal, so that no matter what quantum computation model you have, you can compute it in this quantum computation model. So they have some generic model, like Turing machine, but both quantum computing. So they have something like graph states, and then they realize that these graph states can be simulated efficiently when the underlying graph has small rank width. So rank width is the thing that I've been studying a lot. And so in order to use this thing, so you need to be given the decompositions of small rank width. So what they did is, if the input graph state has small rank decomposition, small rank decomposition of small width, then you don't need a quantum computer. You can use classical computer to compute it efficiently in polynomial time. So that's what they did. And this decomposition can be generated in time and cubed. So this is one instance where people use it. And another instance is this big Meta Theorem. So when you have tree-like structures, you can use that to solve some particular problems. But now people say, well, not only you solve one problem, you can solve many problems at the same time. So this is one type of theorem. So any problem that can be expressible in certain logic called monadic second-order logic of the first kind can be solved in linear time whenever the input graph has rank width most k, and it's given with this decomposition. And the important part is that now we can generate these decompositions in cubic time, so we don't need this line. And then we have to replace this running time by cubed. So here's one example of the logic formula where we want to know whether the graph is 3-colorable. So can I color the vertices in one of the 3 colors so that adjacent vertices get distinct colors? well, how do I encode that into logic formula? Well, does there exist x1 set of vertices, x2 set of vertices, x3 another set of vertices, so that whenever two vertices are adjacent, they are not in the same set, and every vertex is in some set, and etc. Right? So they will if this logic formula is true, that means graph is three-colorable. Otherwise, it's not. So a lot of problems can be expressible in this kind of logic, and so we have this meta theorem. Okay. So that's it for talk, and thank you for your attention. And this is the small advertisement for the website. So please visit the website for DIMAG, so the DIMAG. So this cannot, yeah. So if you Google Discrete Math Group at IBS, you can see the website where you can see the videos of the talk and the list of the future events. Okay. Thank you very much.
이런 현상에 대해서는 어떻게 분석하나요?
그러니까 그래프가 다이내믹해서 시간에 따라서 변하는 경우를 질문하신 거죠. 예. 네. 현재 그런 방향으로 현재는 연구가 잘 안 돼 있습니다. 예, 잘 안 돼 있고요. 아마 그러니까 이게 디컴포지션 관점에서 연구가 잘 안 돼 있고요. 랜덤하게 많이 일어나는 경우에는 사실은 좋은 디컴포지션을 가지지 않는다. 랜덤하게 만들 때는 그런 식의 연구는 있습니다. 그래서 제가 했던 연구 중에 하나는 랜덤 그래프를 만들면 예를 들어 위스 값이 뭐 리니어하다, 꼭지점 수에 비례한다, almost surely 뭐 이런 식의 디어렘도 있어서 랜덤하게 제너레이트하는 그래프에서는 잘 안 먹히고요. 이런 테크닉들이 보통 어떤 경우에 잘 먹히는가 하면 구조가 좀 많은 그래프, 어떤 스트럭처 원래 좀 인헤리트하게 어떤 스트럭처가 있는 상황에서는 이런 인풋 트리 스트럭처를 많이 가져서 사용하기가 좋게 됩니다. 감사합니다.